Alright, so another clip for you guys. I'm wearing my tribute to Robert S. Mueller III, rest in peace. Good old Bobby Three Sticks, former director of the FBI. Anyway, I got my watch, same watch he wore Casio DL290, I believe, and he wears it with the face on the inside of the wrist. It's like military style because you don't want the glare to give away your position while you're walking around, you know what I'm saying? Got that blue pinstripe on. He would rock the Brooks Brothers, but I don't have a Brooks Brothers pinstripe suit with the foulard pattern tie. And of course, we have the Oxford button-down collar white shirt. He would only wear white dress shirts, and he would actually sharply rebuff anyone who would show up to a meeting wearing anything other than a white dress shirt. And it's like I said in the last clip, he literally lived out the embodiment of Ivy League style. So the outfit today is a tribute to Robert S. Mueller III, rest in peace. He is one of my fashion icons. Fashion muse, dare I say. Anyways, another word on my Faraday induction apparatus design. So this is another one of the problems. I just talked about probably in the last clip how I got a more sensitive Hall sensor coming on the way. I'm going to wire in an op amp, that way I can in effect amplify or widen the aperture on the signal range that I'm looking at, because the neodymium magnet is going to produce a fairly strong magnetic field in the coil. This isn't the coil I'm using, but this is for, a prop to give you a visual of what I'm talking about. Magnet goes in. I was thinking I'm gonna have the Hall sensor in the wall of the coil, but this is only on the inner diameter 2¼ inches. So the Hall sensor inside of here would only be like an inch away. And I was having some problems getting like a baseline reading of the magnetic field strength of my neodymium magnet. It's an N52 magnet, 1/2 inch diameter, 1/2 inch height. So that's rated at about like 6,000 Gauss, which I think is like, you divide by 1,000 to get the number of Teslas, so it's like 6,000 Teslas strong. I don't know which unit I should go with, probably Tesla, but okay, the Hall sensor that I ordered was like the most sensitive, widest range one that I could find. And if you're operating that Hall sensor at 5 volts, then the max and min magnetic sensitivity is 176 millitesla. So that's like 1,000 orders of magnitude too small. It's closer to like 10,000 orders of magnitude too small, because, okay, 6,000, it's, basically 10,000 in terms of like scales. It's closer to 10,000 than 1,000. And 1,000 is already 1,000 times larger than the max of that Hall sensor. But the 6,000 Gauss magnetic field strength of my magnet that I mentioned is at the surface of the magnet, because a lot of these magnetic field strength ratings are for like if you stick the magnet to something, you measure how much force does it take to like remove that, essentially. And I guess according to the law of Biot-Savart, which is derived from, I think, the Ampere-Maxwell equation out of the 4 Maxwell's equations, it falls off, magnetic field strength falls off, that is proportional to 1/r². It depends, of course, because like modeling a magnetic field is a little bit complicated, especially for materials, because it's a little more straightforward if you have like a single strand wire that's infinitely long, or you have just like a single loop coil. But then when materials get involved, the geometry of the magnet itself and all that, those things start to come into play. And especially because I'm using a magnet, like I've got it right here. I'm not gonna grab it right now. Well, I might as well. I've taped it to my ruler here to do preliminary tests, okay? 1/2 inch in diameter, 1/2 inch long. This bad boy produces quite the magnetic field, it turns out. So the strength, if I'm not mistaken, is the rating that is at the poles. So it's technically not as strong on the axis of the magnet, but the axial length of this magnet is obviously equal to the diameter. So I was like, should I think of this as like a magnetic point dipole, being that it's at large enough distances, effectively spherical in a sense. But then like if you're approaching the pole of a cylindrical magnet head on to like the normal, as if it's like swinging through the coil, right? That is going to be stronger than when the axis is like coaxial and it's in the center of this coil, right? But like this is still a pretty strong magnet, so it's going to be relatively strong when it's like an inch away from a Hall sensor at the very center of the coil. So I'm like, okay, what I need to do is have a known strength magnetic field to use with that Hall sensor when I first get it. I ordered like 2 or 3 of them just in case I like burn one out or whatever. And if I have a known magnetic field strength, then I can look at the readout and calibrate accordingly. But then also I can then say, okay, if I know that the sensitivity of the Hall sensor is 176 millitesla, let's say, and I have a known magnetic field strength at a particular distance of 100 millitesla, then I can have my magnet centered in the coil and then just move the Hall sensor far enough away so that it's reading 100 millitesla strength of the magnetic field from the actual literal magnet. That way the Hall sensor is not necessarily inside of here, and it'll be a little bit maybe off from the waveform due to the oscillation of my plexiglass protractor attachment, because then when there's like max magnetic field strength and the magnet is in the center of the coil, Hall sensor is further away, so like the distance will be farther away, you know what I'm saying? So that could be a problem. But with all this being said, part of the problem is, okay, well, how do I produce a known magnetic field of say 100 millitesla? And that makes me think that I have to create another coil, and to predict based on the number of coil winds how strong that electromagnet is going to be. And you could either use like, okay, AA, AAA batteries, that's like what, 1.5 volt a piece. You can use like a 9 volt, or I have my 12 volt power supply, which I'm using to power the motor. Still, if I have an air coil, if I just like make another coil on this, I would need like tens of thousands of coil winds, and that's a lot of wire. And as I do that, use more wire, then the resistance of the coil internally is going to go up. So that will lower the amount of current that's in the coils, and the magnetic field strength is proportional to the current that's in the coils, in the wire. So if I wanted a multiplier on that, I would have a core that's not air. And I was looking online at some like magnetic permeabilities of different materials, different metals, and like if you go to Home Depot, most of the like screws, bolts, etc. are stainless steel, which has a relative magnetic permeability of about 1. So magnetic permeability of a vacuum is like 1.2 times 10 to the negative 6 Newton amps or something like that. So relative to that, it's stainless steel has a permeability of like 1. But then iron, for instance, has a relative magnetic permeability of like 5,000 or something like that. So if I had an iron core, then I would have to do 1,000 times less winds in order to get my expected or equivalent magnetic field that I'm going for. So it's kind of like this numbers game of like, well, I can find these cores on Amazon, let's say iron cores, but they're all like 6 inches long, and I need a narrower electromagnet, so something that's only like 1 or 2 inches long, but like ideally 1 inch. Like, this is half an inch, the magnet, right? This ruler is probably like an inch thick. So if it were 2 inches, you know, it might not make that much of a difference, but they only sell these core rods. The smallest one is like 6 inches long. And I'm like, well, it's soft iron, so I could supposedly cut it with a hacksaw, but that's gonna be a big mess, and I don't wanna ruin my hacksaw just to like cut it once and all this stuff. And I think at the maker space, I mean, they do like have a metalworking class, but that's like $150. And it's like, all I need to do is just cut this rod, basically. Or like, I don't know if it's worth like risking, you know, my safety to use like my Dremel with, like, the Dremel could probably do it. I have extra diamond encrusted bits, but like still, it sounds, you know, just the idea of having to cut metal rods is like a little bit sketch, a little bit much, but I'll probably end up doing it anyways. Those rods were like $15, $20, but then I can have the iron rod and say, okay, this has a known magnetic permeability. Wind the wire around, and I can have a known source at a known distance away from the Hall sensor in my target range of magnetic field strength. And then it's kind of like I'm deviating from the original plan of having the Hall sensor inside the coil. I'll have it slightly further away. As long as it's able, like, let's say that the Hall sensor is down here on the ruler, and then here's the coil above it, and this is swinging through. It goes through the center and it comes out the other side. The sensor has to be along the axis right here, directly underneath the center of the coil. Like, if it were in front, then it's not going to be proportional, I feel like, to the waveform of the oscillation out here. You know what I mean? Or obviously, if it's like out here, same deal. We're not going to get a readout on the Hall sensor proportional to what's swinging through the coil. So it's more to try out, and yeah, that's all I wanted to say. Rest in peace, Robert Mueller.